Live from the Benson Building in beautiful Provo, Utah, it is Organic Chemistry. Yay. Oh. All right, welcome. Can folks at home hear? Somebody type yes if you can hear. Yep. Okay, good. Thank you. I've got the chat up on our screen so we can sort of, I can sort of monitor what's going on. It is shown to the whole class though, so if you want to swear or say something unkind about me, you may want to do it now actually in front of the whole class as opposed to later on. But anyway, just be advised. Something unkind, there you go. If you'd have told me that we had been doing this when I started teaching in 2011, I'd have told you you were nuts. Live streaming comments and everything like that. That's fantastic. Okay. Well, there's a few more things I want to do with acid-base chemistry, and I actually just need to go look and make sure I remember where we left off last time. Okay. Yeah, last time we were dealing with how to determine based on the pH of a solution, what the state of various groups would be. And we learned that by comparing pKa and pH, we can determine that. We spent some time talking about not getting tripped up with the equilibria for amino compounds, recognizing that the amine is an acid with a pKa of 38, but it is also the conjugate base of ammonium with pKa 11. And so when you're in pH 7 water, the form that dominates is actually going to be the ammonium. Similarly, you want to avoid getting tripped up with alcohols, which if the pH is greater than 16, I'm not sure you can actually get that. I don't remember. But in any case, alcohols are, in addition to being acids, are conjugate bases of oxonium ions, which have a pKa of around -2. So at pH 7, you would expect the dominant form to be the alcohol. So you need to get good at being able to determine as a function of pH what various groups, whether they would be in their acid or base forms. All right? Yes? Is it true here that you're looking, if it's got to be positive, you're looking for the smallest one? I suppose so. Yeah, if a group has multiple equilibria, you compare the difference, and the difference that is smallest and positive will be the one that you worry about. Yeah, I think that's a decent way of thinking about it. I will say that I don't think there's a problem on your practice exam like this. Nevertheless, I think you should have the skills to do it. And so if you want to practice this, maybe go look up a pKa table in chapter 2 of your text, or perhaps, I call that a mask. Oh yeah, well, that's true. There's somebody on NPR yesterday saying that we should now be wearing 2 masks instead of 1. So yeah, maybe I'll come next time in this mask and my Darth Vader mask. That'll show everybody. All right. So if you wanted to practice this, you would just need to look at a pKa table and ask yourself, for each of those acid groups, if the pH were 7 or 2 or 9, would that group still have its proton? And I think you can work through that in that way. There was a question last time about how to use pKa tables. You can find, as I said, you can find a pKa table in chapter 2 somewhere. I wish I could tell you, but I don't remember. It's also in Appendix A, which has many more acids in it. How do you use a pKa table? Well, it can be somewhat tricky. In order to use it appropriately, it's useful to recognize different functional groups, which is something that we want to do in chapter 3 anyway. In pKa tables, we want to generalize as much information as possible without losing important bits of information. So we're going to, for the purposes of the pKa table, when we abbreviate a group as R, we're going to assume that R is something hydrocarbon. Sometimes in class, I will be sloppy with the R group and mean many different things, but for the pKa table, let's be that specific. So if you looked at a pKa table and saw that with a pKa of minus, oh no, sorry, it's not minus, of 4, then you would not be surprised if you went and saw an enormous and horrible molecule. I'm trying to remember exactly what I drew last time. It made people angry and stressed out. So naturally, because I didn't want them to be miserable alone, I'm redrawing it here for all of you because I'm nice that way. Okay, fine. So I would need to be able, looking at the pKa table here, to say, this functional group looks an awful lot like the one from the table. And therefore, if I had to choose a pKa for that group, 4 is probably reasonable. Okay. It can get tricky with alcohols because not all alcohols are created equal. Ethanol or other alcohols where R is a hydrocarbon have pKa's of around 16. But if you put that alcohol on a benzene ring, the pKa drops to 10. Now that's not a number I would expect you to memorize. You can look it up here. And in fact, I'm going to generate as a PDF, a pKa table on the content page of Learning Suite that you can use on the exam. But could you tell me why this molecule is more acidic? Just so we have names to deal with, this molecule is called ethanol or whiskey, and the molecule below is called phenol, which I think used to be a component of antimicrobial throat spray. In any case, if you had to choose without pKa information, what would you say?
The phenol can stabilize the negative charge better because of the resonance structure.
Right. If you draw the conjugate base for phenol, resonance allows you to move that negative charge around via the negative charge 2-step to generate the following resonance structure. And if you followed that pattern, you would be able to see that I can delocalize the negative charge in the conjugate base of phenol in a few different places. In contrast, the conjugate base of ethanol is ethoxide, which just has the negative charge localized on the oxygen. So sometimes you need to use the tools we've talked about, the whys behind the pKa trends, to make some reasonable judgments. As a result, even if I didn't have these numbers before me, I would be hesitant to say that this OH group and that OH group were the same thing, because their conjugate bases there's a big enough difference in their conjugate bases that I wouldn't expect those to have the same pKa. Now, if you need a pKa value, I'll give you one. And in this case, I did. So it's about 16 here versus 10 here. Amines are troublesome on pKa tables because they come in multiple varieties. You can have the primary amine or the secondary amine. And these both have pKa's of about 38. And that is for losing their proton. But remember that amines have conjugate acid ammonium forms. You've got the primary ammonium, the secondary ammonium. There's actually a tertiary ammonium too. And you can assume that all of those have a pKa of around 11, right? Now, That's not to say that all ammonium groups are created equal. For example, if you take the following ammonium ion, its pKa should be about 11. If instead of a hydrocarbon nearby, you put a carboxylic acid, the electronegativity of those oxygens creates an inductive effect that stabilizes the conjugate base and actually brings the pKa of that ammonium group down to 9. So again, you have to use a little bit of intuition to make sure you're using the pKa data correctly. Again, if you need a specific pKa, I will give it to you. And it turns out I only have one amino group here anyway, so there's really nothing to worry about. But I have had people struggle to discern between the right pKa to use with amines. And I think we talked about that last time. A word of warning, distracting functional groups, which aren't really going to be important in acid-base chemistry. The amide, that's a different animal than an amino group because of the presence of this carbonyl oxygen. So those groups have a pKa, but it's generally high enough to not be important in aqueous solution and to not be important in a lot of organic chemistry. So if you see a group like that, you can ignore it. There is a protein side chain, which is kind of complicated. It's called the guanidinium group. This is the side chain of the amino acid arginine. It looks like this. It's interesting because the positive charge can be delocalized on either of those nitrogens via resonance. It has its conjugate base is the deprotonated version, and the pKa to go from protonated to deprotonated is like 12. So actually, this guanidinium nitrogen is even more basic than you would expect for an amine. Now, I wouldn't have expected you to invent this functional group from scratch. It's just present in nature. I would also not have expected you to be able to predict what its pKa is, but if I put it on a table, you're gonna have to recognize that this is not the same as an ammonium ion. And I've had people make that mistake previously. So you want to be careful in your use of the pKa table to make sure that whatever you find and whatever value you're using comes from a structure that resembles the group on the molecule as closely as you can find. And then be sensible about your choices. If we were to look up that SH group, we would find that it has a pKa around 7. For the proton on the end of the alkyne has a pKa, if we looked it up, about 25. I only know that because I've taught the class for almost 10 years. I used to couldn't say that, and honestly makes me feel pretty old to say that, but it's okay. Time only goes one direction, and you will be there too someday. And we can then laugh at all of the are we going to call them post-millennials? When do we make that distinction? I don't know. All right, and the pK of the amine is 38. So why are we going through this with this strange molecule? Well, because it's easy to answer an acid-base question when it's presented to you in the following way. Okay, and I think maybe I gave this to you guys as a practice problem at the end of one of the lectures. Can you predict which way the equilibrium lies? Except I'm making stuff up here, sorry. So given an acid and a base, you draw the conjugate base of your acid, the conjugate acid of your base. You identify the acids on both sides of the equilibrium. If someone's asking you where does equilibrium lie, you look up the relevant pKa values, and then the strongest acid loses its proton. I used to say the strongest acid wins, but that makes it seem like you get the equilibrium the wrong way. So the strongest acid wins by losing its proton, or just the strongest acid loses its proton. There was a question on the chat. How is this group that I've shown you here different from a regular ammonium group? In an ammonium group, the positive charge is localized on the nitrogen. In this, it's called a guanidinium group, and you don't need to know that. You can delocalize that positive charge via resonance. And so this is a much more stable acid, which makes its base more reactive. We can reason it that way too. Not a key issue to recognize why this is more basic than why the guanidinium has a higher pKa rather than the ammonium, but I thought I'd answer that since it was there. Okay, so coming back to that equilibrium, strongest acid wins by losing its proton. So which side dominates at equilibrium? The right side. The strongest acid has the lower pKa. Boom. All right. Now, another way I might have phrased that question is this base strong enough to deprotonate this acid? And you answer that question by setting up the equilibrium and comparing the pKa's of the acids on both sides. Another way we could ask that question is coming back to the molecule here, and I could ask which protons would be mostly removed by a particular base. And let's choose like an alkoxide. The first thing you want to do here is to draw the conjugate acid and look up its pKa, which is 16. And then you could pick any of these groups and set up your own mini equilibrium experiment. So for the carboxylic acid, let's draw what the conjugate base and conjugate acid would be. Okay, with me so far? Find the acid on either side. We've already identified the relevant pKa's. Strongest acid wins by losing its protons. So can this base remove the carboxylic acid proton? Yep. Ding, 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 ding. Now, you can do that for each one of these individually. Or you can take a shortcut. And the shortcut illustrates this principle. And maybe actually before we do the shortcut, I'll do one more example. Here's your alkyne proton again, sorry. Plus the alkoxide to give you the conjugate base of your alkyne and the conjugate base acid of the alkoxide. We identify acids on either side of the equation. Strongest acid loses its proton, and equilibrium favors the protonated form. So no, the base cannot remove that proton. All right, so what we're seeing as a pattern here is that, and this is something I will say, I'll write it down and then I'll say it again a couple of times. If a base can remove a proton if the pKa for that proton is less than the pKa of the base's conjugate acid. All right, now it sounds like we're talking about somebody's third cousin twice removed at this point. So let's try it again. A base can remove a proton if that proton's pKa is less than the pKa of the base's conjugate acid. That's just another way of summarizing the strongest acid loses its proton. So if you go through it slowly and draw out the equilibria, you're going to always get it right, provided you remember that lower pKa means stronger acid. If you want to take the shortcut, all you need to do is compare 16 with the pKa of whatever you're thinking about removing. If the pKa is less than 16, if that's the pKa of the conjugate acid of your base, and if the pKa you're looking at is less than 16, then yes, your base can remove the proton. If it's greater than 16, then no. So we would say for the amino group, yes or no? No, 38 is greater than 16. So the base cannot remove a proton when that proton's pKa is greater than the pKa of the base's conjugate acid. How about this one here, 10? We're good. Yep, that one comes off. How about the SH group, pKa 7? Yep, that one comes off. What do we do about this annoying situation where the pKa's are the same? If you draw out the equilibrium and the pKa's are the same on either side, guess what? Means your equilibrium constant is about 1, which means that it's maybe half of the molecules are deprotonated and half are not. And that's been a source of confusion in the past, which is why my questions will always have this word mostly in it, where mostly is greater than 50%. All right. So if the pKa's are the same, you'll say, no, it can't completely remove that proton. All right. Any questions on that? Missing anything in the chat? We're good? All right. Kind of messy in the drawing. Oh, well. All right. I think that basically does it for acid-base chemistry. One other kind of question I can ask, and someone asked, I think last time, how would you know or expect that the pKa of phenol would be less than the pKa of ethanol? And you might not know the number, but if you focus on resonance delocalization, you'd be able to predict that the pKa of phenol should be lower and that phenol should be more acidic. Similarly, if you look at this comparison, you might not know that this nitrogen had a pKa of 9, but based on the concept of inductive withdrawal of electron density due to nearby electronegative groups, you could predict that the lower ammonium ion would be a stronger acid than the upper one. So be able to use those principles to make comparisons even in the absence of pKa data. Yeah. Yes. Yeah. It's a good question, and you would think it would. I've tried without success to look up pKa's for amide protons like that. It seems like they're not, I think they probably are lower than 38, but they're high enough to not be important in aqueous solution. So yeah, it's a good question. I suppose you could, the same thing, what you're asking is the analogy in the world of alcohols is, yeah, putting that carbonyl there does lower the pKa of the OH proton from 16 to 4. For the amino group, the pKa is 38. I don't know what it is for the amide proton, but it'll be lower than 38. But I do know it's high enough up that most, if you're in physiological solution, you never worry about it. Yeah. Yeah. Okay, good. What else? All right. So want to say a little bit about nomenclature or naming of organic molecules. And in doing so, I want to give you a bit of a warning. Your goal in this section is to know what you need to know and not pay attention to what you shouldn't need to know. Great, this is what we're all trying to do in life. What do I mean by that? Naming of organic molecules. Why is it useful? Well, the first thing you want to get is when I'm talking about a molecule in class and I use nomenclature terms, I don't want you to be lost. So I want you to have enough of a working knowledge that you're not lost. Of course, we're going to draw stuff, but sometimes we're going to want to do something other than say that molecule right there versus that molecule right there. And so that's why I introduced the term phenol versus ethanol. I don't know why I put phenol in quotations. My Aunt Dinah passed away a month or two ago. She's married to my mom's brother, and growing up, we spent a lot of time over there. Dinah had a tough time with quotation marks. She used them in very creative ways. For example, she threw the bridal shower for Amber when we were engaged, the one that the family was going to come to. And on the invitation, she wrote, come to the bridal shower for Josh Price's fiance, Amber. Amber, if that is even her name, right? So she always did funny things like that. We never knew exactly what she was going to come up with. We figured it was mostly for emphasis, but so if you want to popularize that use of the quotation mark in honor of my dearly departed Aunt Dinah, I'm sure she'd be thrilled. Another fun story about Amber or about Dinah and Amber. Amber's my wife, by the way. Or rather, I am Amber's husband. That's how I should be introduced. Anyway, we were engaged and we were visiting Dinah and Bruce and talking about the reception. And by this point, my cousins, Bruce's children, had mostly grown up and gotten married. And so Bruce, from the perspective of a father who's been through weddings a couple of times, said, you know, I think that you ought to just take the money. I think your dads or whatever ought to just offer you money to not have a reception. You take the money and run. I think that'd be a great idea. We all thought, Amber and I thought it was a funny joke, but Dinah was not amused. She thought that maybe that was a little bit pushy. So she said very calmly, with an undercurrent of menace, Bruce, I'd like to see you in the other room, please. So they go off into the other room while me and Amber are left sitting there. And a few minutes later, they come out of the room and Bruce, thoroughly chastised, says meekly, I think a reception is a lovely idea. So anyway, I could tell you more Aunt Dinah stories, but I needed to kill about 3 minutes. So now they're done. And now we have an interesting use for the Dinah Webb Memorial air quotes usage. Okay.
Someone in the chat just said that her great Aunt Diana does the same thing on her birthday.
Oh, okay. Maybe it's a generational thing. Okay. Maybe we needed to have been born in the 40s and then that would be. Okay. Yeah, we'll have to look into that. Somebody want to go do a research study of improper use of quotation marks originating in 1940s Utah? That might be kind of interesting. Well, so your goal in nomenclature is when I talk about a molecule, you're not lost. And then second, you want to be able to name a molecule clearly enough that someone could, looking only at the name you've given the molecule, draw the correct structure. So this means some things are important and some things aren't important. And I'll try to distinguish between those. Now you've got a fairly thorough description of how to do nomenclature in the study guide, which I don't want to repeat here. But I will give you a few tricks that'll help you sort through what you need to know and what you don't need to know. All right, so there's a sheet in the study guide that sorts functional groups into priority, into a list of priorities. And I found it's useful to think of the priority of various functional groups as being sort of lumped together. So there's a bunch of functional groups that have platinum class, sky, whatever boarding ability, and they're the first in line. And then you have some that can maybe get the first class upgrade if there's none of those other high rollers present. And then you have the rest of us that get to board last, even though we're at the back of the plane. They do that so you have to walk past those jerks in first class while they swill their martinis and laugh at you because you're sitting in the back. Apologies if any of you are those jerks in first class. We don't really think you're jerks, except when you're swirling your martinis at us, but you won't be swirling your martinis as BYU students, I guess. Swirling your milk, seltzer water. I hope you're drinking seltzer water in first class. Well, the rest of us drink Dr. Pepper or something. All right, sorry. On one today. There's a first group, the highest priority group of functional groups is groups where a single carbon has 3 bonds to a heteroatom. Now, among this group, you're not going to need to know which has highest priority because in general, the molecules we're dealing with will be simple enough that there'll be only one example, a maximum of one example from this group in a molecule. If it has more than that, chances are nobody uses the systematic name anyway. So included in this group are the carboxylic acids, 3 bonds to oxygen. For this highest priority elite class, you're going to want to pay attention to suffixes only. Don't worry about prefixes. For the carboxylic acid, it is oic acid. For example, this is ethanoic acid. F because 2 carbons, A for no double bonds, and for ethanoic, and for no double bonds, and oic acid for the carboxylic acid. By the way, nobody in their right mind calls that ethanoic acid. We just use the more common vernacular acetic acid. So now you're seeing why this is not as important as sometimes it's made out to be. Also in this group are amides and esters and acid chlorides and anhydrides. Again, don't worry about the prefixes because these will always be the highest priority functional group, and you're not going to have to determine, oh, is the amide higher or lower priority than the carboxylic acid? There is a rule, but I don't know it, and I don't care if you know it. Okay. The next group, you're going to want to pay attention to both prefixes and suffixes. This group only has 2 members, and it's where carbon has 2 bonds to a heteroatom. There are actually more members to the group, but only 2 that we'll worry about. One is the ketone, and I'm going to be pretty clear here. R equals a hydrocarbon. So this is a ketone, and its more reactive cousin, the aldehyde. Suffix for the ketone is -one. Suffix for the aldehyde is -al. Prefix for both of them is -oxo. So as an example, perhaps we draw a molecule like this. It's got 1, 2, 3, 4, 5 carbons, and let's put a ketone on carbon 3. This would be a pentanoic acid. And since it's got a ketone on 3, we'd call it 3-oxo. Sometimes there are rules about when you need dashes and when you don't. Don't know them, don't care about them. Okay, not a huge deal. What if there are multiple functional groups out here on this chain? What are you supposed to do? I think technically the rule is they're numbered, but you put them in alphabetical order. Don't know, don't care. As long as you have the right number associated with the right functional group, you can draw the molecule correctly, even if it's technically out of order. Finally, the last group in priority is a maximum of 1 heteroatom bonded to carbon, to a carbon, a single carbon. Sorry, in this list are things like alcohols, where and here it's useful to know suffixes for the very simple molecules and prefixes for the more complicated ones. All is the suffix for the alcohol. The prefix is hydroxy, or suffix for the amine is amine. Prefix is amino. And there are some others, which we won't go through. But those are the three groups to sort it in. Within each group, it's pointless to memorize or know what the relative priorities are. Just sort them in that order and you'll be good. All right, a second thing. Oh, can somebody remind me what a heteroatom is? Yes, we are carbon and hydrogen centric in organic chemistry, even though most of the interesting things happens when there are other elements present. Any other element besides carbon and hydrogen, we are going to call a heteroatom, just to be general, because that's faster than saying atoms other than carbon or hydrogen. Okay. What else not to worry about? Let's talk about numbering rules. Technically, you're supposed to number starting with the highest priority functional group, and then you move down the chain in such a way that the maximum number of other groups have the lowest possible combination of numbers. In some cases, that choice is obvious. In other cases, the choice is more difficult. And here is something that I don't care about. So here is a ketone with two groups on it. Technically, the ketone carbon in this cyclohexane ring gets the designation 1, 1, 2, 3, 4, 5, 6. And then I would call this 3,4-dimethyl cyclohexanone. But you could, if you weren't concerned about giving the methyl groups the lowest possible combination of numbers, have started at 1, 2, 3, 4, and 5, and you could have written 4,5-dimethyl. I'm okay with that because it gives you the structure correctly and unambiguously. So don't worry about, well, should I number this way around the ring or the other way? Just make sure whatever numbering scheme you choose, you're consistent and you get the correct structure when drawing it. All right, questions so far? Now, there is one element that's really important in all of this, and it's related to double bonds. Of course, there's nothing to worry about with a simple molecule like this, though nobody uses its standard name ethene. Everybody uses ethylene. And there's nothing special if you only have one of those 4 hydrogens being non-hydrogen. You can write propene, and that's all you need to do. In fact, if you put 2 methyl groups or 2 identical anything on the same carbon, there's nothing special you need to do. 2-methylpropene would be good enough here. And even if, as long as you've got 2 of the same group on at least 1 carbon, the other one can have whatever on it, and there's still no ambiguity. So I suppose you would call this 3-methyl-2-butene or something like that. Starting, I shouldn't number there. 1, 2, 3, 4, whatever. However, once you, if you make it so that both of the carbons in the alkene are attached to 2 different things, then you've got some problems because the following 2 molecules are different, at least at temperatures that we're interested in organic chemistry. Both of these would be called 2-butene, but how do you say that well, one of them has the methyl groups on the same side, one of them has methyl groups on opposite sides. We're going to use, we can use in this case the term cis when they're on the same side and trans when they're on opposite sides. Now, why do we care? The answer is it's tough to rotate around double bonds because remember, double bonds come from side to side overlap of atomic p orbitals to make the pi molecular orbital. And if you break that side to side overlap by rotating one partner with respect to the other, you get to a 90-degree angle and there's no bond anymore. So rotating around a double bond requires breaking really of the pi bond, which in most cases is high enough to be very difficult. I'm going to go to an app called, yes.
So the cis and trans are prefixes, right? So it'd just be cis 2 butene.
That's right. They're prefixes. So yeah, cis 2-butene for the one on the left. And you can use cis and trans as long as whatever you do with it is unambiguous. And that would be perfectly okay for these molecules. I'm sorry for the poor penmanship. Do you know, when I was in second grade, you had to take, penmanship was part of your grade. And I think I got a C- or something like that. And I never really thought my parents were that hard on me, but I had to have a talk with my dad outside in the backyard about how prices like us would need to be more determined than getting C- in handwriting. So still stuck with me. I don't know that he remembers that talk, but I do. He told me a story of my great grandma who'd gotten injured in a car accident and nevertheless had clung to life and come back. And there was some connection. Emma's laughing. There was some connection to handwriting. So yeah, I needed to try harder. So yeah. And they wonder why many of us have depression and anxiety or are on various meds. I actually am on some meds. If you want to talk depression, anxiety, I'm happy to talk that sometime. Meds are good. Go get the help you need, whatever. But yes, there may be a reason why. Oh, right. I was going to show you a fun little app on my iPad. This is Theodore Gray's Molecules. It's actually a book that you can get, but the fun part is what's not in the book, which is these simulations of molecules and their shape. So there's a gallery of molecules and you can click on each of these and look at their structures. So I'm going to choose, I'm going to choose one that has a double bond in it. Okay, fine. We'll choose that one. That's not as fun as the other one, but it'll work. Maybe I'll show you a couple of them. So this is called a molecular dynamics simulation. The white spheres are hydrogen. The black spheres are carbon. The bonds are there in a typical Lewis structure. This is simulated with at, I don't know, 120 femtoseconds per our actual second. So in reality, the molecule will be jiggling around like crazy. And then we can change the kinetic energy of the molecule by increasing the temperature. So if we get up to sort of surface of the sun type temperatures, things get really wacky. We can go down to around room temperature and you get a sense for what's going on with these kinds of molecules. Notice that single bonds you can rotate around easily. You can do a little propeller action, on these methyl groups, and rotation is easy because rotation doesn't change end-on-end sigma overlap, okay? But rotation around the pi bonds is difficult. The purple stuff represents electron density. It's sort of the average wave function squared for all of the wave functions in the molecule. All right, so you see that now I'm going to take hold of that proton and I'm going to try to rotate this around so that it's no longer cis or trans, but rather cis. Okay, and just to slow things down, I'm going to take it down to about 50 Kelvin so that things aren't jumping around too much on us. All right, taking hold of that proton, twist. Okay, it worked, but it wasn't as easy as twisting around a methyl group, right? If I really torque it, but still no, okay, can I get it back to the trans? Maybe. So the goal here is to see that it's difficult to rotate around double bonds. Not that it's impossible, because you can, but unlike what we're doing here, solutions of molecules don't have magic Apple pencils that come down and touch a single hydrogen atom and apply a bunch of excessive force to make it isomerize. Instead, these are just bumping into each other all the time. And so at room temperature, there's not enough kinetic energy to isomerize around a double bond. This can get even more interesting if you look at some other molecules. There's a dye called indigo, and this is its structure. Red is oxygen, blue is nitrogen. There's a double bond in the middle. And this one's a little bit easier to isomerize if I just take a proton on the nitrogen. Well, nope, that actually didn't really want to that much, huh? So let's try the oxygen. Pull it over. Oh, there we went. Okay, but in either case, you're seeing that that rotation is slower than rotation around a single bond. Let me know if you can't see that, because I'll need to retry.
Someone else wants to know if you can rotate around a triple bond. If you have enough energy.
Can you rotate around a triple bond? Well, because triple bonds are linear, you don't need to. You can rotate the groups on either side freely. Yeah. Technically, no, because for the triple bond, if you wanted to rotate those two carbons with respect to each other, they're locked down by 2 pi bonds, and you'd have to break overlap. I don't actually know. It's an interesting question. Yeah. Okay. So anyway, that's kind of fun. And there are a lot of interesting molecules in here. For example, if you want to see a precursor to, no, this is actually LSD. So if you want to see what LSD is, that's what it looks like, kind of. Anyway, kind of fun. In any case, we're going to need because rotation around double bonds is tricky, we're going to need a better way for some molecules to describe their shapes. Now, cis and trans works okay when either carbon involved in the double bond is only bonded to one non-hydrogen thing. But all we have to do is add an ethyl group to our molecule, and suddenly the situation gets more complicated. So this is now a pentene. It's now I guess we would call it 2-pentene and maybe 3-methyl-2-pentene. But lo and behold, so is this 3-methyl-2-pentene. And yet they are different, because in the one on the left, the methyl groups are on the same side of the double bond, whereas in the one on the right, the methyl groups are on opposite sides of the double bond. Cis doesn't work anymore, neither does trans, because those are terms that describe the relationship between two groups. They're relative terms. If I said cis 2-methylpentene, what do I mean? Do I mean the one where the methyl groups are cis, or where one methyl group is cis to the ethyl group? I'd have to specify it. Okay, well, 3-methylpentene, comma, the one where the 2 methyl groups are cis. And then quotation marks for dear Aunt Dinah. Okay, not good enough, right? We're going to have a system of assigning a 1-letter designation that will tell us everything we need to know. It will tell us all of this stuff. But to get there requires a bunch of rules. I will tell you that we're going to call the one on the left E, and I don't care that you know that it's in parentheses, E 3-methylpentene and 3-methyl-2-pentene, and this would be Z 3-methyl-2-pentene. Don't care about where the dashes are or where they aren't. How do we assign that designation? There is a list of rules, and I want you to, before next class, I want you to learn those rules, get good at them, figure out and encounter a few misconceptions and some challenges, and then we'll work some problems next time. Because of all the things in the nomenclature, this is probably the most important. All right, with that, I guess we are done. So have a good afternoon.